Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's videos we learn how to draw shear force diagram for a beam that is subjected to a uniform distributed load. We consider a simply supported beam under uniform distributed load. Let's start with the simplest case. The beam 20-foot length, and here is a pin connection, and here is a roller connection, and the force that is applied, uniform distributed load. Intensity or density of this force is 300 pounds per foot. That's a bit. We want to show you how to draw shear force diagram here. First, okay. The first step is to draw the free body diagram and determine the reactions at the support. Support A, support B. Then the free body diagram will separate the beam from the surrounding. And at A, because of pin joint, we have a Y and a X. At B, we have just the roller. We have a BY only. And it shows distributed, uniform, distributed load, 300 pounds per foot. This is the free body diagram. It's separated from the surrounding. We show reactions at the support. And then, in order to find out reaction at the support, we have to convert this distributed in the free body diagram as a point load. The equivalent of it, which acts in the middle of this rectangle, exactly, is equal to 300 times the length of the beam, which is 20 pounds, is 6,000 pounds. Then neglect the uniform distributed load. We have only reactions at the support and 6,000 pound point load that apply at the middle of the beam. Let's write the equations of equilibrium. First is sigma fx equal to 0. It shows that because we don't have any external force in x direction, then Ax resulted that Ax must be 0. That's the first result. Okay? We do not have Ax anymore. In this case, we must consider the summation of forces in y direction because we have a two unknown. These equations, one equations and two unknown, we cannot reach to an agreement, to an answer. Then let's use the other equation, summation of moments about any of these supports. It says that if I consider summation of moment about point A, for example, equal to 0, it means that force 6,000 times 10 foot here, which is in the clockwise direction, we put it as convention negative, and force By counterclockwise direction positive times 20 equals 0. And solving these equations, we reach that By, we arrive at this result that By is equal to 3,000 pounds. Okay, By is 3,000. Now we can go for the third equations for equilibrium, summation of force in y direction 0. It means a y, we don't know, plus 3,000 By minus 6,000 equals 0. A y is equal to 3,000. Again, it was very easy that I showed that because the load is uniform distributed and we have 6,000 pounds in the middle from the same distance from the both supports. Then I divided it by 2 and 3000A, 3000B, and there is no external force in x direction that we don't have force. But I must write them step by step and show you how I calculated, how I arrive at 3000 for each support. Okay. After that, we return back again by free body diagram, but showing the distributed force again on the beam. 300 pounds per foot, and here at A, 3000 pounds, and here at B, 3000 pounds. Then I wanted to draw its shear force diagram. I choose origin at O and direction of X to the right here. And I chose because the loading conditions we have only one loading conditions, one distributed load. I take the simplest form. A uniform distribution from A to B doesn't change. Because there is no change in the external load or loading conditions, we need only one imaginary cut through the beam. It doesn't matter where. You can cut at here or cut at here, you get the same result. Okay, I cut at here. Then this length, if I cut this length of X. And I consider the left portion of the beam. Any cut divide the beam into two pieces, right side and left side. I here consider the left side portion. My origin is on the left. Then this is the left side portion. And this is 3000. This is the uniform distributed load that is subject, the left side is subjected to that. 300 pounds per foot, and that is X. This length also is equal to X. And because we cut the beam at the internal reactions in the beam, you know there is a shear force of V inside the beam, and there is a bending moment counterclockwise inside the beam. If you consider the right side portion, according to the convention, actually V should be upward, bending moment should be clockwise. That's a convention. When you attach these two together, they vanish because they neutralize each other. And many books consider this direction for V downward and direction for M for the left side counterclockwise. Okay, let's write the equation at C, the cut sections, equation of equilibrium. We know from static, if a whole beam is in static equilibrium, any piece or particle or portion of that must be also in a static equilibrium. Then I write these equations again for this portion. I can write them. Then I started from summation of Fy because I wanted to find out force V, shear force V. Like here, I have to convert this uniform distributed load because I write the equations of equilibrium, uniform distributed load. I have to convert it to a equivalent concentric load that applies to a point. Then the resultant of this 300 pounds per foot will act in the middle of the beam here. How much is it? 300 times the length of this portion, which is X. Then what I have? I have 3000 here upward positive. and 300 times x negative, and minus v, which is v is negative, equals 0. I transfer v to the other side, or I keep v here and transfer the all 3300x to the other side, and I arrive at these equations that when I transfer v to the right side, the minus change to positive, then v is equal to minus 300 plus 3000. That's the equation of the shear force diagram. It is similar to the linear equation of a straight line. Y is equal to ax plus b. You know this is a straight line. Slope can be positive, can be negative. Here the slope is negative. Then let's draw this line. I need only, for a straight line, I draw x-axis. Because it is the shear force, the vertical axis is shear force V. At x is equal to 0 at the origin, V is equal to plus 3000. And at x is equal to 24 or 20, V is equal to, at x is equal to 20, V is equal to minus 300 times 20 plus 3000. V is minus 6000 plus 3000. V is equal to minus 3000. Then choose minus 3000 here at x is equal to 24. That's a point. If you attach this point to 2 points together, here, that one, that's the shear force diagram. In bin analysis, you will find in the other videos that we are looking for maximum V. And you know, for these types of loading, maximum shear force happens at the supports. Here is 3000, other there is minus 3000. And it's a straight line. And for us to calculate, for example, horizontal shear stress, VQ over IB, we are looking for V max, and V max here is 3000. The beam doesn't know anything about minus or plus. It doesn't matter for beam, it's 3000 or minus 3000. It just put in the formula 3000. This is how to draw a shear force in a simplest case. Later, we add some load to this load, and again draw the shear force diagram. Thank you for watching. See you on the next videos.